Now we come to the periodic table and the trends that are present in the periodic table. We'll see that the periodic table, as we know, is divided into groups. We have 8 groups and we have 7 periods. If we look at group 1, for example, we will see that all group 1 elements end up with NS1. If you look, for example, if you look at group 1 elements, for example, lithium, sodium, potassium, rubidium, cesium, you will see that all of them ends up with 1 electron in the outermost shell, but it depends on the number of periods. For example, lithium, we say 2, 1. In case of sodium, we say 2, 8, 1. In case of potassium, it is 2, 8, 8, 1, and so on. All of these elements present in group 1, we'll see that all of them will end up with 1 electron. But as you see here, if we write the electronic configuration of lithium in the SP notation, we'll see that lithium is present, has the electronic configuration of 1s2, 2s1, but for sodium, it is 1s2, 2s2, 2p6, and then 3s1. For potassium, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So rubidium will be 5s1. For cesium, it will be 6x1. So always, the group 1 ends up with S1, but it depends on the number of shell, because lithium is present in shell number 2, in period 2. It is present in period 2. That's why it ends up here with 2. We say 2s1. Sodium is present in period 3. It will end up with 3s1. Potassium is present in period 4. It will end up with 4s1. Rubidium present in period 5. It ends with 5s1, and so on. Cesium with 6s1. But the general trend that all of them end up with s1, but the difference is between the number of the period that they end with. Depending on the number of the period, they are ending up with 2, 3, 4, 5, or 6, depending on the number of the period. So we say that generally, group 1, all of them will end up with NS1. N means the number of the period, or the number of shell. And S1 means the outer electron is present in S1. If we look at group 2, for example, beryllium 4, and we have magnesium 12, we have calcium 20, and so on, strontium and barium, we will see that for beryllium, it's 1s2, 2s2, magnesium is 1s2, 2s2, 2p6, 3s2, calcium will end up with 4s2, strontium will end up with 5s2, and barium will end up with 6s2. So we'll also see that all of them end up with the S2 subshell, but of course, depending on the number of the period, beryllium is present in period 2, it ends up with 2s2. Magnesium is present in period 3, so it ends with 3s2. Calcium present in period 4, so it ends up with 4s2, and so on. So we will see that all group 2 ends up with NS2. All of them end up with NS2. If we look at group 3, for example, we have in group 3, we have boron, which has 5 electrons, 1s2, 2s2, 2p1. We see that it ends up with 2s2, 2p1. This is the last shell. We have to consider the s and the p together, not the p only, because this is the last shell. This is period 2. We have 2s2 and 2p1. We have to consider them both at the last shell, as the last shell. If we have aluminium 13, we say 1s2, 2s2, 2p6, 3s2, 3p1. So it ends up also with s2p1. the last shell ends up with S2P1, and so on. If we take the one below it and the one below it, all group 3 end up with NS2NP1. If we look at group 4 elements, starting from carbon, we'll see that carbon ends up with carbon 6. It is 1s2, 2s2, 2p2. So its last shell contains 2s2, 2p2. Silicon, the one below it, is 1s2, 2s2, 2p6, 3s2, 3p2. So it also ends up with s2p2. And the rest of the elements present in this group will also end up with s2p2. So group 4, all of them end up with ns2np2, and so on. If we go for group 5, we'll see that all of them end up with ns2np3. For group 6, ends up with ns2np4. We said before that the number of group gives us the number of electrons in the outermost shell. So if you add 2 plus 4, you get 6. The elements present in group 7 will end up all with ns2np5. And for the elements present in group 8 or group 0, end up all with ns2np6, because when we add 2 plus 6, it gives us 8. So all groups, all the elements present in the group, in the same group, all of them will end up with the same outer electronic configuration. And we say here n, where n gives us the number of shell or the number they are present in. So if you look here, you will see that this is the trend in case of the number of or the electrons present in the same group. All of them have the same outer electronic configuration. For group 1, it's ns1, for group 2, ns2, and so on, until we reach group 8. Of course, we have 7 periods in the periodic table. Since group 1, all of them end up with the S1, all group 2 end up with S2. So we call groups 1 and 2, we call them S block elements, because they end up with the S subshell. So we call them the S block elements. For groups starting from 3 to 8, you will find that all of them ends up with the P subshell. That's why we call them the P block elements. So the S block elements are the elements present in groups 1 and 2 because they end up with the S subshell, but all elements present in groups 3 to 8, we call them the P block elements because all of them end up with the P subshell. Starting from group 3 till group 8, all of them end up with the P subshell. We call them the P block elements. And since this block, these elements that are present in between groups 2 and group 3, all of them fill electrons in the D subshell, so we call them the D block elements. They are called D block because their electrons are also filled within the D subshell. Now, when we come to the periodic properties, the periodic properties means that when we go across a period or when we go down a group, what happens to the physical properties of these elements? When we look, for example, at the first property, which is the atomic radii, of course, in order to measure the radius of any atom, it was so difficult to measure the radius of any atom because, as we said before, that when electrons rotate around the nucleus in any atom, they are rotating in a wave motion, and this wave motion, or we call it an electron cloud, they rotate around the nucleus in what we call an electron cloud, and it is impossible to know where the cloud starts and when does it end. When you are taking an aeroplane and you are going down to the country you are going to reside in, you will see that the clouds will start and end, but you cannot distinguish where did it started and where did it end. That's why scientists found it difficult to measure the distance or to measure the radius of any atom. So what did they do? They brought diatomic elements, like, for example, hydrogen or oxygen or chlorine, the diatomic elements like this one, it's a diatomic element where the atoms at the beginning overlap together, and they started to measure the distance between the two nuclei, because the nuclei are dense particles. They are present at the middle of each two atoms, and the case of this electron cloud is not now taking place because we are measuring the distance between two dense particles. They are not moving like in case of electrons. And so using what we call X-ray, we can measure the distance between these two nuclei. Using X-ray, they can measure the distance between these two nuclei. And when we take the distance divided by 2, half the distance, we get the radius of each atom. So they did know the radius of each atom using the X-ray method by subjecting X-ray to the molecules, and by measuring the distance between the two nuclei, we can get the distance divided by 2, we get the radius of each atom. Now, when we go down a group, what happens to the distance between the radius of the elements? What happens to the radius down a group? Taking group 1 also as an example, we say that in group 1, lithium has 2 shells to be filled, sodium has 3 shells to be filled, potassium has 4 shells to be filled, rubidium has 5 shells to be filled, and cesium has 6 shells to be filled. So we see that as we go down the group, and as the number of electrons increases, as we go down the group and as the number of electrons increases, more shells are being filled, and so the atomic radius increases down the group. The atomic radii increase down the group because as we go down the group, more electrons are present, more shells are being filled, and so the radius down any group will increase. Okay, what happens across a period? If we look at across a period, what happens? For example, we said that we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now, we said as we go across a period, the positive nucleus increases, the positive charge increases. And we said that there will be more attraction between the positive nucleus and the electrons, the outermost electrons, isn't it? We said that as we go across a period, as the number of positive nucleus increases and the nuclear charge, of course, increases, so the attraction force between the nuclear charge or the positive nucleus and outermost electrons increases. And since the attraction force increases, the radius decreases. The radius decreases. So across a period, the radius, the atomic radius decreases. And this is because all of them fill within the same number of shells, as we said before. They fill their electrons within the same number of shells. We have here in all these elements present in period 2, all of them fill their electrons within 2 shells. But what happens is that the positive nucleus increases, the positive charge in the nucleus increases. The nuclear charge, we say that the nuclear charge increases as we go across a period. And when the nuclear charge increases, there will be more attraction force between this nuclear charge and the outermost electron. And since the attraction force increases, we will find also that the radius decreases. Whenever you have more attraction between the positive nucleus and the electron, the attraction force increases. This means that the positive nucleus will pull the outer electrons towards itself, because the attraction force increases, the electrons are going to be pulled nearer to the nucleus, and so the radius will decrease. So this is the trend in radii, that when we go down a group, we will find that the radius increases going down a group. For example, lithium, sodium, potassium, rubidium, cesium, or whenever we go down any group, we will see that the atomic radius increases. Atomic radius increases, and that's because as we go down the group, the number of electrons increases, the number of shells filled increases, and so the atomic radius increases. It will become bigger and bigger. But across a period, we will find that the atomic radius decreases, and that's because as we move across a period, the positive nucleus increases, the attraction force between the more nuclear charge and the outer electron also increases, and also the radius will decrease. Okay, so this is the first trend that we have to talk about. If you look here, in case of elements down a group, you will see that this is lithium and this is sodium. Lithium is above sodium. So you will see that the lithium has a smaller radius than sodium, because sodium lies below lithium, so it will have a bigger radius than lithium. If we compare, for example, if we compare beryllium with magnesium, you will see that magnesium has a higher or a bigger radius than beryllium. They are present in the same group, beryllium and then magnesium. Since magnesium lies below beryllium, it has a bigger radius, and so on. For all the elements, if you compare aluminium, which is present in group 3, with boron, which is also present in group 3, you will find that the radius of aluminium is greater than the radius of boron, because they are present in the same group. So down the group, the radius increases. But if we compare the atomic radii between elements present in the same group, in the same period, this is period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, you will find that the radius decreases as we go across the period. If you look at period 3, starting from sodium, going to chlorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, you will find that the atomic radius decreases across the period due to the stronger attraction force between the greater nuclear charge and the outer electron. But across or down a group, the atomic radius increases.